Thank you, guys. Are we on? Good. So I appreciate all you guys coming out. Unfortunately, I think most of you are here because the weather has kept you here. But I'm also disappointed that only like 0.0001% of my colleagues showed up. That was supposed to be funny, 400,000 people. So anyways, he said, I'm Robbie Strickland. I lead the Engines and Pipelines team on the Watson Data Platform and also the Spark Technology Center. This is my co-presenter, Emily Curtin, who also works at the Spark Technology Center. She's a software engineer there. We are both from the beautiful, warm, sun-filled city in a forest of Atlanta, Georgia. Just to clear things up, if your impression of Atlanta is the Hartsfield-Jackson North Terminal or the 7585 connector at rush hour, or maybe you've never been and you're kind of surprised we drive cars and not cows, to all of you I say gently, please come back and come see us. We have great music, great southern and international culture, national park with whitewater kayaking within city limits, amazing food and art, great sports teams, although we won't talk about Sunday. Actually, we were going to come wearing Falcons jerseys, and I sent her an email at like 9:30 to that effect, and then we got canned. So, but we won't talk about any of that. So we hope you come back, and it's a lot more than Concourse B. So anyway, today, you guys don't care about that. Today you care about Parquet. That's why you're here. So today we're going to deep dive into Parquet. It's a quiet but powerful tool that will change your workflow if it hasn't already. So I'm going to talk about our reasoning for using Parquet, and then I'll hand it over to Emily, and she'll walk you through the technical details, because of course I'm a VP and she's an engineer. So without further ado, let's talk about storage. Storage. Sounds exciting, right? We've been talking for almost 2 days about all kinds of high-minded things like distributed computing and whiz-bang technology and machine learning. So let's take it down a notch and talk about storage. Why would we do that? Because storage matters. Yes, streaming is cool and important, and yes, we want to think about real-time applications in machine learning, but often we just want to churn and burn through absurd amounts of data to train our models or query for patterns or whatever. So we need to make sure that our data storage is performant, efficient, and reliable, like this Bagger 288 here. So let's define our goals for efficiency a little bit more. So first, what we need is a data lake, right? So let's make a data lake. So what are some good goals for our data lake? Well, first we want to integrate it into our stack. We want our users to be able to figure it out without bothering us too much. We want it to be resource efficient. But we want it to be resource efficient because resources cost real dollars. Real man hours, real compute cycles, and bad resource utilization really impacts our ability to provide fast queries. So really, we want fast queries, and we don't want to spend an arm and a leg to get them. Everything else, it could be considered a bonus. So how do we get this kind of resource efficiency? Well, we get it by sweating the small stuff. The small stuff will blow up when your data gets big. When your data can no longer fit on Emily's favorite flash drive here, and when you're talking more like tens of petabytes of data, like we have talked about in our past experience, than hundreds of megabytes, those little costs add up both in terms of money and compute time. So let's look at I/O time as an example. I/O costs really hurt. And we're not just talking about disk I/O. We're querying in a distributed environment, so we have to get our data off disk and then across the network to our distributed compute cluster. So we have disk I/O and network I/O to consider. It's nanoseconds to memory, but it's microseconds to a solid-state drive, and it's milliseconds to spinning disk, and then it's tens of milliseconds for network. This is definitely a detail worth sweating over when it comes to choosing a storage layer for our data lake. So let's take a slightly opinionated look at some options. This is an opinionated table, so don't flame me for it. I'm comparing 3 options for storage: files, compressed files, and databases. Let's first look at the files. I'm talking TSVs, CSVs, TXTs, JSONs, whatever, so long as it's files. Files are really easy to use. There's no learning curve, there's no administration, you don't have to set up PagerDuty on your files, and they integrate really well with your stack, whatever your stack might be, because everything handles files. Here I'm considering my stack to be just Spark. So where do files fall down? Well, they're big. They're actually enormous and slow. They hurt badly on those disk and network I/O costs. And when you're querying them, the performance is terrible because Spark has to pull in the whole file to pull the columns and filters you're looking for. So can we do better with a database? Well, databases are a great tool, and sometimes they can be the right tool for the right job. But data lake storage is the wrong job. It's impractical and crazy expensive to scale a database to handle multiple petabytes. So yeah, we can get better queries, but now we're paying for servers, for cycles, for man hours to administer it, for your time on PagerDuty. It's a mess. So can we do better than these two options? Can we combine the ease of use of files with the query time of a database? I say yes, we can. Enter our hero, Parquet. This is a benchmark done on a wimpy Spark 2.1 cluster with 1 master and 3 worker nodes. All data in HDFS, and the CSV weighed in at about 420 gigs. You can see we've got 100x speed up between the raw CSV and Parquet compressed with Snappy. And you might be thinking, that's unfair. That's a column selection query. Well, the table scan query looks just about the same. The Parquet formats shuffled around in terms of who is fastest, but we're still close to 100x speed up between CSV and the fastest Parquet. So hopefully I've convinced you that Parquet is your best option for data lake storage. So now I'm going to turn it over to Emily, who will take you into the details.
Thank you, Robbie. So what is this mystical Parquet format? Well, the project will tell you that Parquet is a columnar storage format available to any project, and I will tell you that it's a binary format, so if you just cat it in your terminal, you're going to get mush. There's an API for the JVM and the Hadoop stack, or if you're at the wrong conference today, there's C++ and native Python. It's columnar. It's both encoded and compressed, 2 different processes, and it's machine-friendly. What do I mean by machine-friendly? Let's hang on to that. The best way to learn about Parquet is by example. So I'm not going to take you through the data set we used for the benchmarks. Instead, I'm going to use a very important data set. And if you've never encountered this data set before, I highly suggest you get familiar with it, particularly like the first column, kind of in the middle. What do we have here? We have some strings, different strings, and some data types. I'm going to write this out in 2 different ways. I'm going to use a flat schema and a nested schema. I'm going to hammer on this nested schema point because one cool thing about Parquet is that it can handle arbitrarily nested data. Here I'm just doing some really simple string to int, string to string maps, but it can handle arbitrary nesting as far as you want to take it. So for illustration, here's a really ugly TSV. This is my flat data. And this is my JSON data, and it looks even worse in slide format. How do we write this out? Well, you guys are Spark experts. I'm not going to belabor this too much. We're going to do spark.read, tell it it's a TSV, say it's got a header, and then we're going to take it to an RDD and map over it? Well, we're going to do that because if we don't infer the schema for this, it's going to work, but it'll write everything as strings. So this is kind of an old school way of doing this. There's lots of ways to do this, but I'm going to make a case class with like everything in my schema, and then I'm going to make this awful brittle method that'll break as soon as the guys upstream change their schema, and then I'm going to use that to map over my RDD, take it back to a data frame, and then I just write with the compression as snappy. That's default. I'm just doing that here for illustration, and then out to Parquet. So not too bad, but that schema inference makes me really sad, and it's a lot of typing, and the methods are really brittle, but at least I'm not doing this in Java, and at least I'm not doing this in MapReduce, so it could be a lot worse. So now that we've seen how to write the flat schema, let's take it to the nested schema, because everybody loves JSON parsing, right? Yeah, well, I do in this case, because all I have to do is spark.read.json. It'll pick up on all of my data types and all of the nesting automatically. So If your data is a little messy, this may not work as beautifully as on this slide, but for my data, it works just fine. So again, I just take that out, write option compression snappy, and out to Parquet. So I feel pretty great about one-liners. I don't know about you guys. So now that we've seen how to write this out, let's go to the terminal and see an actual example. Oop, forgot to clear my screen. So in this folder, I have 2 Parquet files.
Can't see it.
Can't see it. Ah, that's a problem. Nope. Sorry, guys. Better?
There we go.
All right. I have 2 files here, but I'm kind of lying to you when I say that because these are actually folders. So I have a little success message from Hadoop, and then what I'll call a compressed file. It's compressed with gzip in this case. So if I just want to crack this open and look at it, it's going to be a bunch of compressed garbage because it's a binary format and it's not made to be used like that. So instead, I can pull out some special tools. And there we go. This is Parquet tools. This is available for free as part of the Apache Parquet project. You can download it, compile it, run it through Hadoop. So you can see I've got all my columns catted out really nicely. So if I come here and hit the back button for 5 minutes and then do meta, I'm going to see all of my metadata for this Parquet file as well. So that's all I wanted to show in the terminal. Let's go back to the presentation. Okay, so we just saw that in the terminal. We've got a little bit of an intuition for it. Let's dig into what that schema actually is. So it's pretty obvious that the first column is going to be our column names. Oh, and I didn't show you the nested schema in the terminal, but there it is for reference. So I've got my column name, I've got whether it's optional, required, or repeated. Optional and required, whether or not it's null, that's what that means. Repeated is what it sounds like. The data type, in this case it was binary. If it's binary, we have some encoding info. And then these repetition values and definition values. This is where Parquet is borrowing really heavily from Google Dremel. Dremel was a system designed to do arbitrarily nested fast query storage. Sound familiar? So I'm not going to lay into these R values and D values too much. You can think of the R values as whether or not this column is repeated and at what level of my nesting it's repeated. So we can see, in this case, links is a repeated column, and we're going to have to dig down a little further to get that repetition. Definition is how far we need to dig in the nesting to see whether or not that individual piece of data is going to be null. So if you want to talk about this later, I'm happy to, but I'm going to leave it there for now. You can see down at the bottom, there's, you can read all about this. Just for emphasis, here is one Parquet row, 2 different ways. Again, I'm hammering on this nesting because Parquet can handle nested data. So now that we have this all written out and we've seen it in the terminal, how do we query it? Y'all are Spark experts. You've probably seen this a million times. So I'm going to read it in from S3 in this case. Create or replace a temp view. There's lots of ways to do this. This is just one. And then at the bottom, run my SQL queries. 2 slightly different queries, same result. In Zeppelin, about Zeppelin, which makes me happy. So hopefully you've got an intuition for how this looks, how we work with it. Let's talk about how it works. So I'm going to take us to the 30,000 foot view, then we'll dig all the way down into the details, and we'll fill up the in-between. So stay with me. Here's our 30,000 foot view in the file system. So I've got my folder, as we just saw, a little success message from Hadoop, some common metadata and metadata. I'm putting these here for illustration. These are schema summary files written out by Spark, and these are actually turned off by default in more recent versions. I'm faking a partition file here. We'll talk about that later. The meat and potatoes is these compressed files, once again. So this is the high-level view. All the way down in the details, let's talk about what we're doing on disk. So with this really simplified table, I'm going to, if I was writing this in the row-oriented way, I would have on disk, string, different string int, string, different string int, all kind of mixed together. And this is tough on our cache. When we read stuff into our like L1, L2 cache, it's not going to be very aligned. Also, if values are null, we may get some branch mispredictions. That's going to be unfriendly to our processor. So a much better way is to write this out in a column-oriented way. So I have everything from column 1, everything from column 2, everything from column 3. I'm not storing nulls. It's all right there, all the same, roughly the same size, and it's much more friendly to our bits and bytes kind of hardware level stuff. Another thing I get from this columnar storage is I'm getting this data that's of similar property, and that means I can pull out every single encoding and compression trick in the book to squeeze this down as much as possible. So let's take an example. Let's look at incremental encoding. I can store album titles, Led Zeppelin 2, on and on for 58 bytes if we don't get technical about delimiters. Or I can store just what we need for the first string, just what we need for the second string to derive the second string, and so on, and that's a 58% reduction. Another example, let's look at dictionary encoding. So these record labels, I've only got 2 of them, so why don't I make this tiny little lightweight dictionary, and then I can take 84 bytes to 10 bits and squeeze that down into 2 bytes, and then I've just got this little dictionary that'll get amortized as my data gets bigger. So there's lots more of these encoding schemes. I'm not going to walk through them all. That would be boring. And we haven't had our coffee break yet. So you can, again, there's a link at the bottom if you want to see more. Let's take it from, so we saw the file system, we saw the details. Let's fill in the in-between. Parquet has, within each compressed file, there's a tree of structures. So this diagram is a tree. And we're going to start at the root node, which is the file metadata. This is where we store our schema, our thrift headers, offsets, some other stuff, number of rows. So for the next part, the row group, let's think of ourselves as Spark nodes. And if I give you 1,000,000 rows to write, you're not going to write all 1,000,000 rows at once. Let's just consider the first 100,000. You know, I've got this group of rows. It's a row group. It's exactly what it sounds like. So from that row group, I'm going to consider each column individually. And I'm going to cut these columns up into chunks. 2 important details here. If an individual value is null, I'm not going to store it. If a whole column is null, I'm also not going to store that. Why would I bother? So you need at least 1 column chunk per column that has a valid value. You can see up here in the example, column 2 has 2 chunks, the others just have 1. Within that column chunk, we'll have a shared page header, which brings us to the main event, which is pages. Pages are the indivisible atomic unit of Parquet. We've got a little bit of metadata, some R values and some D values. Another detail, if we have a flat schema, we don't store those because they're all the same. And then where we came from just a minute ago are encoded data. So encoded data walks all the way up the tree, and then that all makes a compressed file. And if my diagram confused you, or if you want to read more about it, there's the non-slide friendly version of the actual format spec, and you can see more of that on the web. So now that we see how Parquet works, let's talk about how Spark works with it to get some efficiency. How do we make those queries so fast? Well, the first thing is that, like any column store, we're going to pull in just the columns that we need. And that's common across any column store you're going to use. The next thing is that we can write using partitioning. This is not entirely unique to Parquet, but the API provides for a really nice way to do this. So I can write .partition by whatever columns I want. A really, really common case, partition by year, month, day, hour, time series. So another thing we can do is Spark will take our queries, and if they have filters on them, it's going to take those filters and push them down into the data scanning process. So I'm going to borrow an example from some of my colleagues at IBM. I have this query where I want between 1200 and 1200 plus 11. So I'm going to push this down to the column chunks, because the column chunks have statistics like mins and maxes, where I can evaluate this filter condition and see, do I even need to pull in this column chunk? If the max is 800 and I'm looking for 1200, I don't need that column chunk. Maybe I don't even need that whole row group. So this is a huge level of I/O savings and all kinds of savings we get there. Just to put some intuition on this, this is a physical plan for the query I showed you a second ago, reading it from a CSV source. There's a big struct, it's really ugly. You're not supposed to get anything from this slide except that it's big. Here's the plan for reading Parquet. Again, there's a bunch of stuff, but what I want to emphasize is pushed filters. This is where we're pushing those filters down, and you can see they match exactly what we were looking for in that SQL query. So to summarize that little section, we're going to get just the data you need, just the partitions you need, just the columns you need, just the chunks of those columns. And you're thinking, this is the best thing since sliced bread. This is wonderful. What's the catch? Because there's always a catch. So there is a catch on this pushdown filtering. It's not going to work exactly correctly when you're using an object store like S3, because there's no random access, and we have to do that initial network I/O to pull that over before we can dig into it, and then it'll work. Pushdown filtering doesn't work on nested columns yet, and there's a whole binary versus string deal, which means that it doesn't work on strings for the moment, but it'll work on numeric fields, booleans, that kind of thing. Some people would say that the next limitation of Parquet is write speed. And to that I say, who cares? Because in most cases, this is going to be write once, read forever. And writing Parquet is fast enough. You know, we do have to do some encoding and compression, and that takes a while to do, but it's worth it because you get such fast reads. So the other thing I want to talk about is immutability. These compressed files, you can't just crack them open and manipulate them on disk because of all the headers, all the offsets, all that tree of metadata that'll be invalid if you try to mess with it. So effectively, these are immutable. How do we get around this? There's a couple different ways. We can say write using partitioning. We can reimagine our data as a time series, for example, and append more partition folders. We can do something that we do at my former home of the weather company, comma, an IBM business, and front this with Cassandra. So data comes into Cassandra, and when it's sufficiently historical, we spool it out to Parquet. Or we can do write mode append and add additional row groups with their schema embedded as file metadata. So how does this work in the streaming context? This is an ongoing thing on the Watson Data Platform. It's pretty similar to what I was talking about with Cassandra. So data comes in until some watermark condition is met, time, size, number of rows. We groom it, and then we write those groomed rows out to Parquet and just append them as additional compressed files. I'm running a little shy on time, so I'm not going to talk about tuning and tips, but these slides will be posted, and you can see those later. So let me skip straight to the summary. Back to this chart. Hopefully, you'll agree with me at this point that Parquet is cheap, fast, wonderful, amazing, etc. And in summary, Parquet is a binary data storage format that, in combination with Spark, enables fast queries by getting you just the data you need, getting it efficiently through encoding and compression, and keeping much of the work out of Spark. And with that, I want to thank you all for coming, and I want to open it up for questions.
Thank you, Emily and Robbie. Give them a big hand for braving coming from Atlanta and facing a hostile crowd in Boston. No, I'm just kidding. Yes, please, go ahead. We've got 5 minutes, so we've got ample time.
What's the encoding strategy? So there has to be a default encoding, and then how would you do a manual encoding override? Is that possible?
That's an interesting question. I'm not sure if there is a way within Spark to do manual encoding overrides. Most of the time, it's definitely done automatically, and we just let Spark and the API pick for us.
Is it sampled? Is that how it determines the encoding?
That is a great question.
Okay, we're just going to alternate back and forth. Go ahead.
How does Spark compare to ORC?
I get to open up my extra slides. ORC is also a columnar format. It's indexed, and it doesn't handle nested data. So those are the differences. Not better or worse, different. Some of the benchmarks I've seen, the table scans are a little bit better with ORC. In selected columns, I've seen the Parquet ones, but really what I've seen is that these benchmarks are really, really old, and they're using old versions of Spark and old versions of the specs, so I don't really trust them. So there you go. There's some information about ORC.
Thank you for the question, Shed. Get the slides. Brilliant. Go ahead.
Hi. What if your data is already time series? You mentioned that one way of dealing with immutability is by using time series layout for Parquet. What if it's already time series? How do you apply changes to a point in time?
So are you talking about once you've written the data, how do you go back and fix it?
Yeah.
So I'll answer that. So the reality is this is the hardest problem. And we could probably spend a significant amount of time just talking about that. We've had no choice in that case but to have, we actually literally have a process that goes back and rewrites the Parquet using a sequence of updates that we have fed in and automatically goes and regenerates. So there's not really a great way around that. The only thing that you can do is if you write your data sufficiently granular enough that you can isolate where you have to do that. So if you, for example, are writing very large files with large amounts of time in them, obviously you're going to have to write more when you go back to regen. We call it Parquet regen. We have a word for it, but it's something that we have to do quite a bit.
Okay. Thank you.
Thank you. Go ahead.
Hi, nice talk. If your data is inherently kind of binary, byte array type things and maybe not be as amenable to the encoding and compression type techniques, is there any real gain or win for using Parquet over a straight kind of HDFS file or some kind of other binary format that doesn't get fancy with its storage?
Well, is your binary data oriented into columns?
Yeah.
And so that's where you'll get your gain, because the predicate pushdown capability will allow you to only extract what you need. Okay. So you don't necessarily get the encoding benefit or compression benefit that you might with strings or ints or whatever, but you will still get benefit from just extracting the data that you need as opposed to getting everything.
Okay, so currently I'm using something like a Cumulo where my scan settings kind of do a similar thing on their tablet servers and only send me the stuff that kind of matches it, but that doesn't obviously get me in the SQL space.
That's right.
Okay, thank you.
Go ahead.
Nice talk, thank you. I have a question. Since Parquet is a columnar format, if you wanted to do append of an extra column, does it support that?
Yes, so that is something I forgot to mention, so thank you for the question. Another benefit of a columnar store is that you can evolve your schema on the fly. So these compressed files all have a schema contained in that file metadata. So in your next compressed file, it'll just have a slightly different schema. There is a big asterisk about schema merging when you're reading. That's usually something you can turn off. But the short answer to your question is yes.
I would also add to that column additions are usually something that you can deal with, but keep in mind that just because the format can handle like a change in columns or deletions or whatever, you want to be careful that your application reading it can also handle it. Mm-hmm. So that's a big caveat too.
Thank you.
All right, we don't have any time for any more questions, but again, give a big hand to Emily and Robbie. Thank you, guys.